Okay. Hello everyone, I'm Namiko Saito from Waseda University. I will give a presentation on how to select and use tools, active perception of target objects using multimodal deep learning. Before we start, let's think. What do you want robots to do if you will live with them? Many of you may think it's nice if robots can do housework, and moreover, robots are expected to support alongside humans, such as medical and nursing sites, dangerous or understaffed sites, and a lot of places. But how to make robots work in various humans' environment and support various tasks? We think tool selection and use is one of the solutions. We humans usually select and use tools depending on the target. For example, when we serve food, we select a tool and adjust handling depending on the ingredients. To deal with various objects, recognition of the characteristics is critical. Extrinsic characteristics are visible, and intrinsic ones are perceived by proprioceptive and tactile senses. Especially if we cannot recognize intrinsic characteristics, we may fail to move heavy objects, class soft objects, or slip low friction objects. To allow robots to use tools, we focus on tool-object action relations and active perception. Tool-object action relations are important not only to understand the tools themselves, but also to understand the object and detect which tool to use and how to handle it. Active perception is a way to recognize the characteristics of the target by capturing the time series changes in the sensory information while directly interacting with the target. In previous studies, they realized robots to control tools to transfer objects. However, they don't select tools. Like this video, if robots cannot select tool, there are some tasks they cannot complete no matter how hard they try. There are some studies tackled on tool selection depending on target. They recognize the object with visions and select tools to pull, hit, and swipe. However, they only considered the extrinsic characteristics. Like this video, if robots don't adjust movement considering the intrinsic characteristics, they fail in tasks. So, there was no work realized tool selection and use considering both extrinsic and intrinsic characteristics of the object. To solve the problems, we proposed two approaches. At first, we construct a deep neural networks DNN model which realizes object recognition, tool selection, and handling seamlessly with the same model. And second, we allow the robot to recognize object characteristics by active perception and tool-object action relations. As an example, we set a food transfer task, which requires to recognize both extrinsic and intrinsic characteristics of various ingredients. The method is as follows. At first, we control the robot and take training data. At this time, the motion for active perception is every time the same. The robot perceives characteristics by different behaviors of the ingredients during directly acting on. We designed the motion by testing several steering ways and finally adapted swinging a spatula which brought out the most differentiated sensory data. The motion of tool selection and handling is remotely controlled by the experimenter. Second, the DNN model is trained, and its latent space. It expresses object characteristics and tool-object action relations. In addition, the model learns to generate the suitable actions. Finally, in evaluation, in experiment 1, we check if the robot can serve untrained ingredients by itself. And second, we check the role of each sensor by changing the combination of the sensor data as input to the DNN model. I will show how to conduct active perception and motion generation of tool selection and use, which is the novel, original point. At first, we control the robot to conduct 4 tasks from steering to pouring ingredients and collect training data. Second, the DNN model is trained and it learns to express the object characteristics and tool-object action relations in the latent space. At last in evaluation, after steering, that is the same swinging spatula as training, the DNN model conducts active perception and explores the latent space value by minimizing the error between the predicted sensor data and real sensory input. The latent space, which is the initial value of context neuron, is updated by backpropagation through time. Then, the robot, using the explored latent space value, the robot generates motions for selecting and transferring by itself. I've explained the DNN model with two modules. The CAE compresses raw images, and MTRNN generates the next time step data based on latent space value. In the MTRNN, we make the initial step of slow context nodes, CS0 to be the latent space, by training the value at the same time with weight during training. As for the robot control for active perception, the robot moves according to the prepared motor command of steering. Then, on the other hand, the robot moves according to the output angle data from the MTRNN step by step and select and handle tools. This is the setup. We tested on a humanoid robot next stage and collected and used its joint angle, image, tactile, force, and grip strength information. The data length and the table setting is as shown. These are the tools and objects. We prepare the spatula for active perception and the turner and the ladle as selectable tools. We prepared 6 training ingredients with different shape, color, size, weight, and friction. And we collected 48 training data, changing grip strength and inclination to scoop. For example, when the robot serves the bread, it grasped the turner strongly and tilted a lot because the bread was heavy and easy to slip. Whereas we used 9 different kinds of ingredients for evaluation. From this slide, I will show you the result. I present the principal component analysis, PCA, on the latent space. Each task CS0 is colored depending on the ingredients. As a result, the same ingredients are clustered. And in particular, the axis of PC2 expresses the proper tools to use, and the axis of PC3 expresses action information. This shows the model self-organized the object characteristics and acquired tool-object-action relations in its latent space. Then we examined unknown ingredients. For example, milk with number 7 is placed near rice, so we expected that, we assumed that the model predicts milk has characteristics similar to rice and proper to be handled by a turner and with grip strongly and tilted with large inclination. So we conclude that the DNN model recognizes characteristics, the tools to use, and the way to act, even the ingredients is unknown. Next, I will show the exploration of CS0 value by active perception. Just after the steering, the time series of sensor data is input to the model, and the model explores the latent value. This graph shows an exploration of untrained milk. The explored value converged, and they became similar to the ones of rice. Therefore, the robot must predict that milk has characteristics similar to rice. I will show the robot transfers untrained milk, and this is the images predicted by the DNN model. Via active perception using sensory input during steering, the robot recognizes the characteristics as similar to rice. The images are generated based on the training image data of rice. The robot collectively selects the ladle, strongly grasps the tool, tilts largely to scoop the milk, and pulls it to the bowl. The robot might think that, the object has a color and shape similar to rice, but the weight and viscosity are different. Well, I can manage it based on the experience with rice. This graph shows the motor angle. The dotted lines are the training data of rice, and the solid lines show the generated angles. As can be seen, the angles are almost the same, but sometimes shifted. So, in other words, the robot adjusted the movement according to the characteristics and the real-time situations. We will show movies observing other untrained ingredients, which are seen at the first time. The robot successfully selects the tools to use and adjusts the way to use the tools depending on the ingredients. Even if the robot uses the same tool, the grip strength, tilt angle, timing to scoop, and speed to pour are changed according to the characteristics and the real-time situations. This slide shows the result of experiment 2 checking the role of each sensor data. The success rate with all the sensors, image, force, and tactile was the highest. When we input only image or force and tactile combination, the success rate of selecting tool is low. It can be said that image and either force or touch is necessary at least for active perception. Comparing to grasping, if there is no tactile input, the success rate dropped considerably. Therefore, tactile contributes to successful grasping. Surprisingly, even though we place the tools every time the same way, many trials failed if the model lacks any of the image, force, or tactile. As for holding and pouring an ingredient, input of force plus tactile failed in all the tests. Thus, image is necessary to handle the tool. In addition, without the force, the success rate became especially low. So force data contributes more to perceiving intrinsic characteristics than tactile. We can say a variety of multimodality realizes rich perception for adaptive tool use with variety of objects. I will conclude the work. Our objective is to realize robots to select and use tools depending on extrinsic and intrinsic characteristics of the object. As a result, with the DNN model introducing active perception and tool-object action relations, the robot succeeded in tasks with unknown objects. We have also found contribution of each sensor data. In future work, we make the robot itself change the steering method depending on the object instead of the constant swinging spatula. And second, we are trying to generalize the tools that can be used. We believe we contribute to the realization of the robot which can support humans in our daily lives. Thank you for listening.